Hola a todos, ¿cómo están? Bienvenidos a otro Talk Series de AMLCS. El día de hoy contamos con Alberto Carrassi. Él está en este momento asociado al Departamento of Meteorology en University of Reading. La charla que nos va a brindar es Data Assimilation from Dynamically Based to Data-Driven Approaches. Bienvenidos todos y espero que disfruten esta charla. Adelante, Alberto.
Hola a todos. Can you see my screen?
Yes.
Okay, perfect. Okay, thank you, Elias, and thank you, everyone. I cannot see you, so of course, it's this is what we are living in this new COVID life. So we are giving, we are learning how to give a lecture without looking at the audience, which is a bit strange. Anyway, so I decided to put together for this lecture a number of results and studies which have been developed in a number of years. Many of them have been originated and motivated by different reasons than the one that I'm using to tell the story that I want to tell today. The story that I want to tell today, it follows, however, a bit of my own research interest and result, and try to put them within the following storyline. On the first part, I will primarily say how methods for assimilating data can be designed by acknowledging the specific property of the model that we are using, in a way or in another, which I will clarify hopefully later. In the second part on the talk, on the other hand, I will talk about more recent study, which have been, of course, encouraged by the recent development of machine learning methods, whereby we try to combine data assimilation in order to make them relying a bit less on the model and a bit more on the data, which is the reason why I say data-driven. Again, I hope to clarify what these statements are about in the course of the talk. Excuse me. So this is a bit outlined, which, as I say, I will spend hopefully no more than a few minutes to remind what data assimilation is in a nutshell. I'm pretty sure that all of you, or a significant portion of you, know what data assimilation what it is, and then I will talk about these two venues, one on how to design data assimilation methods which are dynamically based, so which are informed on the property of the model, and the second part on the data-driven, so on how to combine data assimilation and machine learning together. At the end, rather than being given conclusion, I rather plot like a sort of forward-looking and try to picture what the situation of the data assimilation is in the field, in my opinion, at least. So data assimilation, of course, it's everybody knows that it's a term which is being coined, has been initialized in the field of the geosciences, but obviously the fields of data assimilation is much broader than the geosciences. In mathematics, this is usually referred to as state estimation theory, or optimal control, or Bayesian inference, depending on how one wants to frame the problem. But more specifically in the context of geosciences, and even more specifically in the context of numerical weather prediction, this has been a discipline which has been strongly motivated by the need to essentially to provide good forecasts. And from the very beginning, the challenge was the one of combining a number of observations. I hope you can see my pointer. A number of observations which are very diverse, very sparse in time and space, and of course they are noisy, and in most of the cases they are also indirect. So they do not directly measure the quantity of interest. And on the other side, because we have a sufficiently good knowledge about the physics which govern the flow, this knowledge then turns out into numerical models which are extremely complicated, extremely high dimension. So the problem of data assimilation was try to combine these two sources of information in the best possible way. And there are many ways how data assimilation can be seen. So I don't want at all to convey the message that the only way to look at data assimilation is from a Bayesian perspective. However, I will provide that perspective here because, in my opinion, is the clearest, and to some extent is the one that I tend to prefer. So one way of looking at the problem of data assimilation from a more abstract point of view is the one of estimating the probability density function, in particular, a probability density function of the state of interest, which I refer with the capital X here, conditioned, so taking advantage of all of the information which is embedded in the observation given by Y. So formally, the problem is the one of estimating this conditional probability under a number of hypotheses, namely the one that the model is assumed to be Markovian, and that the error in the prior and the error in the likelihood error in the data is not correlated. The problem is the one of estimating this object here, so as we can sequentially update the data. So this sequentiality is very important in data simulation for geoscience, because in general there the problem that we have is the one of estimating the state of a system which evolves in time, and as long as the system evolves in time, new data becomes available, and we want it in a way to update and to take into account the new data which becomes available. This is illustrated in this figure here, in which we have the time, we have the PDF, which are picturized in 2 dimensions here as a function of time. So we have the truth, which is what we wanted to track. We have the model, which because of the chaos, which again I will tell a bit more later, tend to deviate. And then we have the information from the data, which is pictured in red, and the process of the analysis, which will eventually take our estimate closer to that of to the truth. Now, this is very nice. This is very, very, very clean. But of course, it is very well known that we cannot afford the full Bayesian problem in systems which have the size that have those encountered in the geosciences. And I will say that because of this obstacle, together with the needs to provide a good forecast for societal benefit, has been one of the enormous push for all of the stream of research which we have seen in the last 2 to 3 decades. And this I won't show anything about that, but I think I can tell you that something that you probably know, that the most of a significant component of the amelioration of the weather forecast that we have seen in the last decades is also due to the data simulation component, and not just to the improvement in our prediction model. So some approximation is needed, and this is so the story of how this approximation have been shaping the data simulation in the last decades is pictured in this time arrow here. So in the 70s, we use optimal interpolation. Then in the 80s, the problem has been framed as a nonlinear optimization problem, which has finally made possible as to assimilate directly data which were, for instance, the satellite data, which were indirectly observing the system. And this has led to the flourishing of these methods, which are known as variational methods, which are very nice, very clean. They are very complicated in some way because they need to, as you probably know, they need to solve a nonlinear optimization problem. Therefore, they need to have access to the derivative of the model, so the tangent linear and the adjoint model, which are very difficult to compute and to maintain to some extent. The 2000 have been the years of the explosion of this Monte Carlo-like method, which are very popular at the moment, which are known as ensemble Kalman filter, ensemble smoother, in which they, in a way, try to extend to a sort of nonlinear Monte Carlo framework the classical Kalman filter result for linear system. We are currently in the situation in which these 2 families of methods are being merged together, giving rise to what are known as the ensemble variational method, in which, in a way or in another, the power of the ensemble method, including the technological power inherent to the ensemble method, is being incorporated into the variational method. The particle filter are, on the other hand, a very, very powerful way. There are a number of different flavors, a number of different family of particle filter. What they try to do is to attack the problem specifically under this Bayesian formulation, because I forgot to say that all of these methods until the particle filter, they all rely on the Gaussian assumption. Now, it is an interesting discussion per se to the extent to which the Gaussian assumption is a right one, but for the sake of the presentation here, I just wanted to convey the message that that is a key approximation. That approximation is very robust and allows to reduce the size of the problem from estimating an entire probability density function in 9 dimensions to that of estimating the mean and the variance, so the first 2 moments of the PDF. Obviously, the covariance for a system of that size still is a matrix of very high dimension and still is a metric which will require some sort of simplification. So some of the challenges that are popular in the field of data simulation for the geoscience have been listed here. As I say, the size of both the climate models and the environmental and the observation is very big. So this is a very big data problem. thanks to the Gaussian hypothesis, we are able to derive computational Fordel method. And the other important point is very much within the dynamics and the process that we try to describe, which are nonlinear and chaotic. And I will primarily work, and I will primarily talk about this aspect of chaoticity and how this has been shaped into data assimilation method. So in the first part, as I say, I will talk about, this is the beginning of the first part of the talk, I will talk about how we can, in a way, shape our data assimilation method by taking into account what the model is. So the first line of research in which I've been working goes under the name, I will say, of data assimilation for chaotic dynamics. So the chaotic dynamics means, of course, as you probably know, at least if we reduce ourselves to the deterministic chaos, imply that we have a high sensitivity to the initial conditions. So eventually any small error that we will do will evolve by making our prediction very bad. This is, of course, is a problem. It's clearly a problem, which means that we need to do a very good estimate of the initial condition. At the same time, however, there is a property of most of the natural system, which on top of being chaotic, they are also dissipative. And this dissipation, in a way, induces sort of dimension reduction. So it is true, the dynamics of the system is still be chaotic, so difficult to track. However, these dynamics will factually take place in a dimension which is much smaller than the full phase space of the system. So the idea that I was pursuing was then, okay, if this is the case, do we have an indication, do we have a fingerprint of this existence of these unstable subspaces in the course on the performance on the ensemble Kalman filter, on the ensemble Kalman smoother? And eventually, if that is the case, maybe can we use this, the presence of the unstable subspace in order to compute the data assimilation within that subspace and therefore attaining a sort of computational economy. So we were first investigating this in the context of linear Gaussian system. This is very nice because we can analytically solve the problem, and we had a number of results in the past which all together try to convey the following picture: the picture that if you have a Kalman filter or a Kalman smoother in linear dynamic with Gaussian error for a system which is unstable, then the projection of the forecast error covariance matrix will converge to that subspace, meaning that the limit of the difference between the two objects will be zero. So this is very important because, and this is, sorry, let me say, this is illustrated in this figure here, which says as a function of time, so as a function of the counting on the simulation, is the projection of the eigenvector of the forecast error covariance matrix onto the Lyapunov vectors, which are a measure of excuse me, of the instability of the flow. So what matters here to observe is that as time goes on, the actual number of eigenvalue which are significantly larger than zero are only bounded to be 14. So we started with the system of dimension 40, yet at the end we discovered that the forecast error covariance matrix of the Kalman filter is only confined in a system of dimension 14. So these opened the path to say, okay, maybe if this is the case, this idea could be exploited to design reduced rank surrogate of the Kalman filter. Now, before moving to that, we need to investigate the extent to which this result will actually expand to the case of nonlinear systems. So this is done here. Again, we are using a Lorentz system of dimension 14, which possesses a number of unstable and neutral direction equal to 14. And here in this plot, you see in the first heat map here, you have the angle between the ensemble subspace, which is essentially the space within which the assimilation will take place, and the unstable subspace as a function of the noise in the data, which gets larger, and the interval between the observation, which gets here. So what we observe here is interesting, is that when we have a strong constraint from the data, by either reducing the noise associated to them or by making them more frequent, the angle between these two subspaces gets to zero. What this means in practice is that the ensemble is factually already looking into the relevant unstable subspace. The integral version of this figure is given on the right here, where we have the ensemble size on the x-axis, the angle between the two subspaces given in purple, and on the left side side y-axis, and the root mean square error of the analysis on the right-hand y-axis. And what is important in this figure is that you observe clearly that the performance of the filter measured here by the root mean square error becomes very good. So the error goes very close to zero as soon as the number of ensemble members reach the value of n0 plus 1. So this means that in practice, there is already a sort of dimension reduction taking place automatically in ensemble common filter in deterministic dynamic. So this idea has been exploited in a system of much higher dimension, of dimension 10 to 5, which again, because it is a dissipative system, possess only, I will say, 24 non-negative Lyapunov exponents. Here we have perform the following experiment. We have a 3D bar in black, then we have a 3D bar to which we also compute one unstable mode along this trajectory, and at each assimilation time, we take the proximity of the maximum of this unstable mode, and we assimilate all of the data which are within a given radius from the maximum of these unstable modes, using the form of this unstable mode. And this gives rise to the method called 3D bar house. So the additional computational cost to a pre-existing 3D bar amount to only the computation of this unstable direction. And we compare that with an ensemble common filter with 30 members. And very nicely, we see that we get a performance which is as good as the one that we get via using an ensemble common filter. So this means that, in fact, we can take advantage in ensemble in the data simulation of the information from the information of the instability of chaotic dynamics. Now, how this picture change when we move to coupled system? All of the examples that I mentioned before, I was talking about uncoupled data simulation. I was talking about a system possessing essentially one single scale of motion. Now, the problem is, how did the picture change when we move into systems which are multi-scale, as it is in fact the case of a system which we encounter in geosciences? This has been studied using this modular arbitrary order atmospheric ocean model. So now we have the coupling between the atmosphere and the ocean, a coupling which is done via two mechanisms, thermal and mechanical mechanisms. The nice things about this model, this is a spectral model, but the nice things about this model is that we can arbitrarily change the number of modes in one compartment of the other. So this is very functional for us. So I've been studying 6 of these configurations of different dimensions, from 36 to 56, and of 2 types of coupling, either weak couplings, when the 2 compartments, atmosphere and ocean, are only weakly connected together, and strong coupling, when they are very strongly connected together. So this is a snapshot of 3 of the main variables. So the string function, the second component of the string function for the ocean, the second component of temperature for the ocean, and the first component of the atmospheric string function. Of course, I cannot plot the full phase space in this case. And you can see here the difference between the weak coupling and the strong coupling. Interestingly, already visually, you see that when the coupling is not very strong between the 2 compartments, the attractor of the system, which is shown here, clearly resemble the attractor of a chaotic dynamics, because we cannot really identify anything than randomness there. When the coupling gets stronger, the system still has a clear feature of chaoticity, but at the same time, we observe a sort of 2 regimes. So the system seems to shift within one regime to another, one regime which is a sort of active regime where the variance is larger, followed by a regime of we say passive regime, in which the variance is smaller. Another important feature of this system, which we found it very important to study from the perspective of data simulation, is that when I increase the size of this system, as I say, from 36 to 56, I plot the spectrum of Lyapunov exponent here in this panel here. What you clearly see is there, the first most important striking difference stands on what we refer to be the quasi-neutral mode. So this system cannot possess more than one single neutral mode. This is just from theory, because it's a continuous system. However, the presence of the coupling seems to make appearing a number of quasi-neutral modes. Quasi-neutral means that they are very close to zero, but they are either asymptotically positive or negative. I'm sorry. Now, what are the consequences if I wanted to do coupled data simulation in a system which has this property? What are the consequences from the point of view of the design and the performance of the data simulation? In order to answer this question, we made another type of analysis. We compute the covariant Lyapunov vector. I'm very happy to answer more technical questions, so please forget me if I'm not being very detailed during this talk, but I want to give the overall picture. However, the covariant Lyapunov vector are vectors which measure the instability. They are covariant with respect to the tangent linear dynamics, and therefore they are considered to be very relevant about the fundamental property of the dynamics. So, observing how they project on the states vector can provide important information about the nature of the instability, which ultimately are those that we wanted to track. So these two panels here represent the projection of the different Lyapunov, covariant Lyapunov vector along the system state, which is of dimension 36 in this specific example. That's why it goes from 0 to 35. The two different panels are related to the weak coupling and the strong coupling on the right. The things that I wanted to remark here is that if you concentrate in the very unstable modes or in the more stable modes, well, then you clearly see that the projection along the different component of the state vector is clearly separated. So it seems that the very high instability are either driven by atmosphere or either driven by the ocean. However, when you move into the region of the quasi-neutral mode, which is this band that you can observe in both cases, then the projection along the state vector get very smooth, meaning that simultaneously ocean and atmosphere are participating to the dynamics associated to this quasi-neutral mode. This is an indication, and on top of that, this effect of smoothness is even larger when the coupling between the two subcomponents is getting higher. So this is an indication, in our opinion, that if we wanted to perform data simulation, we really need to take this direction into account. So we really need to do a coupled data simulation. Now, how the picture that I showed before, this one will change in coupled dynamics. Now, this is investigated here, in which we have, again, the angle between the ensemble subspace and the unstable subspace in a panel of, sorry, there is a label missing here. This is the error in the observation, and this is the frequency in between data. And you see that, again, you have that feature that we observed earlier, in which the angle gets smaller when we reduce the error, for instance. We reduce the error in the data. So, but what is interesting is that so if you look at this angle, this pattern and the root mean square error pattern, they don't look each other at all, as it was the case on the system which were uncoupled. On the other hand, when we include in the computation of the unstable subspace also all of the quasi-neutral mode, the modes that we would have discarded because in principle, they will not participate to evolving instability, then we have the resemblance that we observed earlier for the uncoupled system. Again, this is then condensated in the figure that you see at the bottom here, which show the ensemble size on the x-axis and the angle and the root mean square error respectively on the left and the right y-axis. The root mean square error, which the only thing that at the end of the story really matter when we perform a skill analysis on the ensemble common filter, is given in the orange curve here. However, when we compute the angle with the unstable neutral subspace only, this is what we observe. So we see that there is not such a convergence that we observed earlier, meaning that there is an important part of the uncertainty which is described by our ensemble that has nothing to do, which is not only confined in the most unstable direction. This, on the other hand, seems to be the case when we include also those unstable, near-neutral modes that I mentioned before. Again, showing that in the coupled data simulation, the emergence of this quasi-neutral mode seems tantamount of the coupling and therefore need to be accounted for when we perform the data simulation. Now, all of this has been done in the case of a system being completely deterministic. We know, however, that this is only an abstraction because model have error, and the typical way how error is included in Bayesian formulation is by using a very simple additive stochastic version. So what we studied here is what is the effect of simultaneous effect of the injunction of noise via the term eta and the presence of instability. Again, what we see here is that if we look at how is the error in for instance, the fifth and sixth direction, which they will correspond, in fact, to direction that will be completely stable in the long run. So direction that you will not take into account according to the picture that we got so far. We see on the other end that because of the noise, these these are the bounds of the error, okay? On this top panel. These bounds of the error get very high. So there is still a portion of the error that we cannot longer ignore because of the presence of model error. We cannot longer ignore the projection of error on the asymptotically stable direction because the presence of model error via the injection of eta and the fact that this asymptotically stable direction are locally unstable, and this is the projection of how they are instantaneously positive or negative, and eventually upwell this error and make our system to underestimate the actual error. So this is what we try to explain here as what we call it the upwelling effect. I will try to be very fast on this, so I don't want to bother with many detail. But to understand what we are talking about, you need to decompose the evolutionary, the tangent-linear error, the tangent-linear dynamics into subcomponent that we refer to the filter error, which is the only thing that your filter will look at, the unfiltered part, which is what your filter is actually ignoring because of your sampling error, and this error, the off-diagonal term, which actually was provoked the upwelling from one term to the other. So what we analytically observe for linear system and then illustrate for nonlinear is that there is an upwelling effect, which is given in this red term here, which is what take error from the unfiltered to the filtered part. This upwelling is not only due to the presence of model error. This upwelling is a consequence of the sampling error. So it's a consequence of the fact that we are solving a system of a given dimension by using an ensemble of smaller dimension. However, the presence of model error makes this upwelling to be very, very, very important. The result of that is that we need inflation. So this means that ultimately, and this I won't give more detail because I want to get up to the end of the talk, the quantification of the underestimation that we will do whenever we have a sampling error together with the stochastic additive noise is measured by the difference between the red and the blue curve here. So the red curve is the error that we will get whenever we perform a Kalman filter only confined on the unstable direction. The blue curve, on the other hand, is an ideal standard extended Kalman filter that actually solves the full recursion that I wrote here, that also include the upwelling effect. So this is the difference that usually we mitigate without knowing it, but we mitigate it by using inflation, which essentially is a trick that artificially increases the covariance explained by our error covariance max. Again, I can provide all detail at a given moment if you ask me a question. I will jump this now. Now, another way to look on how, setting apart now the chaos, another way on how I have been interested in trying to design data assimilation methods which were connected to the model property has been in relation to model error. As I say before, for many reasons, many of those reasons are very good, we tend to describe the model error in data assimilation as a stochastic process. However, and this, as I say, is a good reason because of the multiple presence of different sources of model error, which are very complex interplay among them, all this makes very convenient and very coherent with the Bayesian framework to express that error as a stochastic noise. However, in many realistic cases, this actually is not the case. And in many cases, in fact, the model error is that fully correlated in time. So I was interested to see how can I include a sort of correlated model error, time-correlated model error in the data simulation framework. In order to see that, consider two systems. So imagine that this is your model, and imagine that you have the true process that you want to describe, which is given by two scales, and this is the subgrid scale that you are not describing in your model. On top of that, you also assume to have a parametric error, which is given by the difference these two lambda. It's a simplification, however, I think it gives you the idea of what I'm talking about. Now, The real evolution error, the covariance error of the system, of the difference between these two, is given by this equation here. So we already see that the important fact which control the error, how the error in the model will evolve in time, is indeed the difference between this object. What are these? These are the tendency. This is the tendency of our model, what we know, what we can compute in our computer, and this is the unknown tendency of the truth that we wanted to estimate. So we would like to have this difference. Of course, we don't have it. So we can, the first point, before doing that, let's assume that we have this. I can approximate this equation, which of course I cannot solve in practice, but I can approximate this equation by making a simple short time Taylor expansion and up to the first non-trivial order. This happened to be the second order. So I can now say, okay, a suitable approximation which I can incorporate within my data simulation is the one of assimilating my model error as a fully correlated in time process within the time window, and which is quadratic in time. But again, the key problem is that we need to estimate this difference here. The idea that we exploit, when we will exploit that later also toward the final part of this talk, is that we can estimate this difference by using the analysis increment. So the idea here is that we have a reanalysis which has been already run, and it represents the best proxy of the data, of the reality that we have. Once we have that analysis in hands, by this approximation, we can estimate the tendency, and then we can incorporate this tendency in the estimate of the model error that we have here. We have done a number of different, we have tested this approach in a number of different cases. I will only show one result here. This is in the case of a model of land surface, which assimilates data of temperature and humidity at 2 meters on the atmosphere, and the model, on the other hand, describe the soil and temperature and moisture content. And we are comparing here, so our approach, which is referred to as short-time augmented extended Kalman filter, is given in blue. So you have the root mean square error of the 4 variables of the model in the 4 plot and the 4 top panels. And then in the bottom 2 panels, you have the absolute error in the respective albedo and leaf area index, which are 2 parameters of the model that we are simultaneously estimating. This type of approach can be incorporated in another type of data simulation too. And in fact, we did it. We did it in a variational method too, but I won't show this now. A final idea, which goes along the line of designing a data simulation method which acknowledges the property of the underlying computational model, is in the context of adaptive mesh model. This is a completely different problem. This is a problem in which the model that we have are, for a number of reasons, solved using an adaptive mesh. So a mesh with change in time according to some type of rules, which can be of any sort. We are primarily interested in model which use a Lagrangian mesh. So a mesh which moves nodes using the velocity field of the dynamics. In particular, we were motivated about that because we were working with a state-of-the-art sea ice Arctic model called NCEO, which solved the mesh in the way that I mentioned. So the nodes of the mesh moves around with the velocity field. This is very important because this allows to describe feature of the fracts on the sea ice, which because they are very anisotropic and they have a very long spatial correlation, that will be very difficult to describe using a fixed Eulerian grade. What the problem is that usually this adaptation of the mesh goes together with the remeshing procedure, in which when nodes get too close to each other, some node is removed and some other node is added in order to maintain numerical accuracy. So as I say, this is the type of model we are talking about, and this is a snapshot. This is a video, but I won't show the video now. It's a snapshot of these models, and this shows how you see the grid is triangular, and you see the grid of different size. If you will see the video will show how this triangular will change in time. They evolve. Some triangle, when the angle gets very close, then they are removed, etc. So, but this is a problem for data simulation because you cannot easily use variational method, because that will make the computation of the gradient very difficult in such a grid. You cannot straightforwardly use ensemble method, because this will make each ensemble member having a different mesh with different number of nodes on different position. So this is the problem that we were tackling here, and with this we developed a new method called sort of projector ensemble Kalman filter. We made two types of approach, an approach in which called high resolution, in which we define a reference mesh, and on this reference mesh, which has a resolution which is related to the computational property of the underlying model, we projected each ensemble member, we perform the analysis, and they come back on the original individual meshes. The key point here was that can we also update the mesh? So this is a sort of philosophical question, in the sense that, obviously, if I make an observation, I want to update the physical quantity in my model. But has the underlying mesh, which moves along the flow, to be updated too? We believe so. We think that it's relevant because the mesh is in fact driven by the velocity, which is indeed a part of the physical component of the model. We did so. This is a snapshot again of the same model, which show the heat content and the sea ice thickness, and you can see clearly, qualitatively at least, how these features are very elongated and very stretched. And here we show an example of this application. I'm focusing on the bottom panel only. You have the Z component here of one direction of this model, and then you have the gradient in blue, and the root mean square error. Sorry, it's excuse me. Yes, the gradient is in blue, and the root mean square error in red. And the reason why I'm showing this is to see that when we update also the meshes, we not only reduce the error in the physical field, but we also improve the spatial gradient, which is a very interesting property when we wanted to conserve physical quantity, as it is the case in realistic physical system. As I say, I will give more talk on that. So this is, I think, conclude the first part of the talk. In the second part of the talk, if I have time, I will talk about a completely different approach, which is, as I say at the beginning, motivated and encouraged by the recent development in machine learning. Now, this is an entire other topic, and I will deserve a larger premise, which I don't have the time to give now. So I have made this very simple illustration to see what this work is about. The important point that I wanted to tell you now is that as opposed to what I have shown so far, here we say, okay, let me try to design a data simulation method which do not rely that much or do not acknowledge that much the property of the underlying model. So in this arrow here, you have data simulation on the left and machine learning on the right. You see that data simulation is classically very good in using a model which is perfect or assumed to be perfect to some extent, but it is very good to handle imperfect observation, intents like being sparse and noisy. We also know that data simulation is able to deal with imperfect model. This usually deals to the problem of parameter estimation, but not only. At the opposite side, you have the machine learning, in which they don't make any hypothesis on the model. They don't have any God in a way. They only have data, but they assume those data to be very good. So they are not that good to describe any other feature which is not already encapsulated in the data set they have been designed to train for. And we wanted to do, it is possible to show, we show it in this recent work with Marc Bouquet, that you can do a sort of data simulation without model error, but you still need to assume a sort of form of your model. And in this work here, we assume that the model is given by ODE, and we try to estimate the coefficient of this. But this talk is primarily about this sort of hybrid area here, in which we want to design methods which are a combination of the two, in which we wanted to make possible that machine learning can deal with imperfect observation. And in order to do that, we will use data simulation. So the idea here, as I say, that we have observation in this way, and we wanted to estimate this underlying dynamic using the data that I mentioned here. There are two complementary goals. One is the one of estimating completely in the model HAM, and the second is the one of estimating some parameterization of the subgrid processes. So for the first goal, emulating the model by combining data simulation and machine learning, we design a method of this sort in which we initialize the weights of a neural net. Then we use that model within a data simulation step, which estimate the analysis by using observation which are sparse and noisy. And as an output, it provides the analysis, but also the uncertainty given by the forecast error covariance, the analysis error covariance matrix. And then we iterate it. Then this output is given in the machine learning step. The machine learning step will update a new coefficient W, and the process is repeated until convergence. I want to be a bit faster, so I won't give much detail, but as I say, I'm happy to answer any question. This is a snapshot of how the algorithm that I illustrated here works and how the two components, data assimilation and machine learning, dialogue to each other. Results are given here. This is the real system is given in blue. This is the power spectrum density, so it represents a sort of long-term property of the system as a function of the frequency. So the blue represents the true system that we wanted to estimate, and the surrogate model, which has been obtained by this combined machine learning and data simulation method, is given in the two other curves. After one single cycle is given in gray, and at the end of the convergence is given in the orange. You see that the classical problem is the one of estimating the higher frequency, but this is something that it is typical, I will say, of many machine learning methods. Interesting also the fact that we also get the very first peak at the very beginning, which seems that is a sort of underlying periodicity that our method is able to catch. For the second scope, which is the one of estimating the subgrid scale, here is a bit tricky, the problem. Here we assume, okay, I have a model which is quite good, I don't want to change that model. I have many reasons why I don't want to change that model. But of course, I still have a component of the subgrid scale that I need to parameterize, because those unresolved scale will drive up the signal in the resolved scale that my model is describing. So the idea here is, again, to using a combination of data simulation and machine learning. This is a sort of snapshot of how the proposed approach will work. Again, we will use the physical model. So I insist only the physical model, the one that is already given to you, to assimilate the data. Then we use a strongly coupled ensemble Kalman filter to produce an analysis. And this analysis increment, and I come back to what I mentioned earlier in this talk, the analysis increment is used as a target in my machine learning procedure. And again, the reason for that is because we assume that the analysis increment is encapsulating most of the information about the model error. And then once I have trained my neural network, which depending on the case, I have used a convolutional neural network or a multi-layer perceptor, as I say, I don't give much detail now, I'm sorry. And then once I have constructed my hybrid, subgrid model, I sum them to construct my hybrid model. So what about the performance? Here I'm using the MAOM system, the same that I used before. I have the truth given by a system of dimension 56 with 20 modes for the atmosphere and 8 modes for the ocean. My truncated model, on the other hand, has 10 modes for the ocean and 8 for the atmosphere, making it a total dimension equal to 36. So there are 20 high-order atmospheric modes which are missing in my model. In my truncated model. And here you say that the error of, this is the error on the second component of respectively stream function of the ocean, temperature of the ocean, and the first component on the stream function of the atmosphere. And you see that the coupled DA-MR hybrid has reduced the error significantly. There are many other things to say here. The first important that, as you can see, the time forecast is given of 2 years in the ocean because it's a very slow process as opposed to the 1 day that we have for the atmosphere. The point to say is that the improvement is larger for the ocean, if you observe this, as compared to the atmosphere. This seems to be strange because it is in fact the atmosphere that is missing some mode. However, at the same time, we know that on the one hand, the machine learning methods are not that good in replicating higher frequency modes, and on the other is a sort of proof of the enhanced representation of the coupling between atmosphere and the ocean, which is thanks to the fact that we are using coupled data simulation. So again, we see how data simulation is able to add feature that will be absent from the pure data, and therefore enabling machine learning to describe more processes. A general view on that is given here, in which we show the reconstruction of the attractor on a plane, which is given by the second component of the oceanic stream function and the first component of the atmospheric stream function. We have the true model here and the truncated model on the top right. You see that the truncated model is not only not describing this sort of bimodality here, but is also visiting a large portion of the attractor which do not belong to the true model. So don't pay attention to the bottom left panel, concentrate only on the bottom right panel. You see here that our hybrid model, on the other hand, Of course, it still has the problem. It's not a perfect reproduction of the truth. It cannot be. However, we clearly see how the unphysical part of the phase space are now less visited, and the higher frequency of visiting is present in the area which were originally present in the true model. So I think it's very promising on how this hybridization has been conducted. So no, I will skip this. I don't think it's important now. So let me go to the very end. As I say, rather than giving conclusion, I wanted to give just a snapshot of what I think the challenge has on the situation. So this is given by this very simple plot in which I put the model grid size on the x-axis and the prediction horizon on the y-axis. I also depicted some typical, I will say, ocean atmosphere processes as a function of these two quantities. You have the turbulence all the way up to the seasonal to decadal. And of course, you can see that we are approximately here now. So you see that as long as the model grid size gets smaller and smaller, we are more and more pushed toward the methods which abandon the Gaussian hypothesis to some extent. And this is, in fact, what is happening in the history of data assimilation. We are primarily here. So there is a lot of interest into investigating how we can abandon the Gaussian hypothesis, because that will be probably emerging as long as the resolution of our model increase. At the same time, however, when we move our prediction horizon more in the future, we need to incorporate other processes of the physical system that we will not have coupled originally. For instance, if you wanted to make weather forecast on 1 week, you can well only have a very simple model for your ocean, or not having your ocean at all. But this is not the case, of course, when you want to get to seasonal to decadal prediction. So you see that when we move along the y-axis, this makes more and more evident the needs of coupled data assimilation. Naturally, all of these two things together, so long time horizon, a high resolution, clearly highlight the fact that we need to have methods which are able to deal with big data processes. And again, this is another area in which I think the interplay between machine learning and data assimilation can be very, very powerful. I will stop here because I think that I'm a bit over time, and I will take any question. Again, I'm sorry if I've been a bit fast, but I wanted to give the full picture before answering any question. Thank you.
Okay, Alberto, thank you very much for your very, very nice talk. I think it was interesting to see how you take us from the very, very basics of data assimilation, then passing through machine learning, and then we have the application, right? How we can improve results. We have some questions in our chat, but I have a first one right now is, well, point of view, you have a numerical model, and that numerical model, you encapsulate the physics and dynamics of the phenomena, right? And then you have machine learning, you have information, some past or historical data, where you partially encapsulate also information of the dynamic of the system. So do you think that the improvement is because when you incorporate this historical data, you are filling the gap of unspecified physics?
This is not what I think is net. This is okay. What we want. This is what we want, but this is not what I think it will happen automatically. Because in order for that to be possible, obviously the data may contain information that they are not encapsulated in our model. That's a fact.
Yes.
And in fact, we have a lot of data, or more than what our model are able to describe. However, those data are not dense enough, spatially and timely, in order to accurately represent a good data set for most of the data of the machine learning method. This is what motivated us. We say, okay, if I use data assimilation to handle those data, which have enormous capital, but they're not complete enough, may I use the output of data assimilation as the input for the machine learning step?
Okay, I see. I have a question with regard to the neural network that you showed before. Well, I saw that you basically iterate on the analysis and then you reinforce with a neural network, right? And then until you merge to something. Okay, that's excellent.
So we in the first part in which we were the goal was the one of designing a full emulating model. Okay, So we compare essentially the machine learning based on the data. So we give the data, we take this model, we suppose that data are only partial, so they observe only a component of the full of the
okay.
And we give those data to a convolutional. So we use two types of network, but in particular for the Lorentz system, we use the convolutional neural network. Now, we compare this approach to another approach in which we say, okay, before doing that, I'm going to treat those data using data simulation first. But what is the model that I'm using for the data simulation component? Well, that model is the model which is estimated using machine learning. And that is the way how it is iterated. So at each iteration, you have a reprocess of the data, but at each iteration, you have a new model because you have a new set of weights for the neural net, which is the outcome of the previous iteration of the machine learning.
Okay. Okay, see. So, yeah. Well, we have two questions. Well, we have many questions. So please, Laura takes some of the questions and put into the screen. So we have one from Randy Steven Consuegra. What guarantees us that the low resolution grid dynamics will behave the same as the high resolution, especially talking? Yeah.
Thanks for this question, Randy. I don't know why there is no guarantee of that. I'm not sure why you are asking me this question, because maybe at some point, maybe in my talk, I gave you the impression that I was saying that. No, there is not any guarantee. And also, of course, in order to answer more specifically, I will need to understand what you mean by behave the same. There is no need for these two scales to behave the same, but there is this belief, which more and more I myself not even considering to be so true, for which when we increase the resolution, the number of processes that we are going to unveil will increase, their interplay will increase, and therefore whatever we have is going to be less Gaussian. Well, it is. I think it is. There is a lot of reasoning behind this process, this way of thinking, but probably it's not that the view is not that simplistic. If you look at the data simulation problem, because the data simulation problem is at the end what we really matter in the data simulation process is the Gaussianity or not of the posterior. Rather than the Gaussianity or not of the prior. Obviously, the two things are connected, but because there is the likelihood in between, the likelihood, in many cases, at least for observation which are linearly related and Gaussian, that likelihood has a sort of regularization. So in this way, you have the two scales behaving in the same way.
So this Randy is one of my master students, Alberto. So he knows
nice to meet you.
Work. Yeah, he knows very well. He's a big fan of you, actually. So, okay.
No.
So we have another question.
Mejor no serlo, Randy. Mejor no serlo.
We have another question from Laura. We have another one from FGA Sevedo 1996. That's a very. So, what would be the repercussions of having poor quality data? How could you deal with this?
I didn't talk about this in this talk, and the repercussions are of any sort. Obviously, as you probably know, when we insert data in data simulation process, we have to provide also an estimate of the error associated with this data. This is a very general word error. There is a very simple instrumental error, but there is up to a very complex problem of what we call the representativity error, which is the way how, because of the mismatch between the scales that your observations somehow are resolving and those that your model solves. So all these together set a problem in the quality of our data. This is a general problem, of course. And in practice, in the real system, in the workflow of the operational data simulation, the data, they go through what they call the quality control before being used into the data simulation process. At the same time, however, you can already understand that properly estimating the error covariance matrix of the data is per se an important line of research. There is many people working on that. We have been also working on that to some extent. That is very much a problem of parametric estimation. So how can we design data simulation method that not only estimate the state of the system, the parameter of the system, but they also update the estimate of the error covariance matrix. There are many people that are working on that. To mention the work by by Dick D, by Manuel Pulido, many others. There is also a very recent review paper on how to estimate the forecast, the observational error covariance matrix and the model error covariance matrix by excuse me, a moment of I will remember in a moment. I will tell you. Okay.
Okay, good. So we have another question. Well, so basically Felipe is also a master student, Alberto. He's a very So we have another question from Hugo Franco. So there is a straightforward approach to introduce the underlying processes from the atmosphere dynamics and ocean-atmosphere interactions into the machine learning models.
It's a good question. I don't know. I don't know that. I don't know if there is a straightforward approach to introduce underlying process. So first of all, you are assuming here that the underlying process from the atmosphere. I think that you're posing the question in this way because of the specific type of example that I have shown. I think that more generally, the problem is the one if there is a straightforward approach to introduce any sort of faster process that we are not resolving into our model. Now, this is an important line of research which has nothing to do with what I have shown, and it exists since long, and is what in general is what we refer to the physical parametrization. So this is the problem of how to describe the parametrization of the faster scale which will not resolve, and usually, of course, the atmospheric one will be the faster. And this is very much the idea of what they call the statistical approximation, and they are based on the assumption that the system has a sufficient temporal scale separation such that the faster scale saturate at a level for which, from the point of view of the slow scale, can be seen as a statistical process. There are many people working on that. I think that the work by John Arlin, the work by Georg Gottwald, for instance, just to mention a few, which are very much on, I think they are set the basis of the now classical theory of how to parameterize the fastest scale into the slow scale.
Okay, excellent. I think, Alberto, thank you very much for your talk. It was very, again,
muchas gracias.
De hecho, los chicos aquí están emocionadísimos escribiéndome que cuando de nuevo, que es impresionante, ¿no? Sobre todo por...
No, me quiero disculpar he intentado daros una perspectiva general y esto inevitabilmente me ha obligado a ir un poco rápido. Entonces ahora, en el mismo momento que daba la charla, me daba cuenta de algunas partes que quizá no eran necesarias, pero espero que haya habido, que el mensaje, digamos, se haya transmitido. Hay toda una efervescencia de cosas, y vosotros sois un grupo muy activo en uno de los tantos aspectos de esta disciplina. A mí lo que me interesaba era, por supuesto, promocionar mi propio trabajo, pero intentar contar una historia de cómo yo creo estamos viviendo un momento de transición debido a esta explosión de Machine Learning, y tenemos que absorbirla, yo creo, con humildad y pero también con una cierta rigor, porque obviamente hay muchas cosas que están teniendo mucho éxito y que son muchas veces cosas que conocemos dentro de un contexto de la asimilación de datos bajo otros nombres. Entonces, yo creo que nuestra misión debería ser de saber elegir las cosas nuevas importantes, saberlas incorporar. Hay muchos problemas, incluso los problemas en los cuales yo sé que vosotros estáis trabajando, donde quizá este tipo de métodos pueden ser interesantes a usar, etc. Lo que me interesaba comunicar era esto, que ha habido un largo momento en que se ha hecho un gran uso de modelos, ahora lo queremos abandonar, pero quizá no queremos tanto abandonar. Esto es un poco...
Exacto. No, de hecho, nosotros también estamos trabajando mucho en el tema de Machine Learning con Data Assimilation. También en AFIT, el grupo de modelamiento matemático, están trabajando el tema desde el punto de estimación de agentes contaminantes.
Esto, por ejemplo, es otro aspecto muy interesante, muy interesante.
Sí.
No sé si habéis visto que ha habido un workshop muy importante, diría yo, porque yo he aprendido mucho, al SNWF, organizado por el SNWF por la ESA, a principios de octubre. Lo puedes ver, y todo está disponible, y ahí yo creo una buena picture, yo diría, de lo que es el state of the art de estos métodos en la disciplina environmental. Si no lo has visto ya, quizás es una buena lectura.
Excelente, excelente.
Bueno, chicos, muchas gracias.
Bueno, muchísimas gracias. Chévere la charla.
Un buen día. Chao.
Esperamos
Desde Colombia,
apoyarnos en un futuro no lejano. ¿Listo?